In case of balance of mass, we started from this total derivative. We said that this is the physical principle, d dt of the total mass, which was this, inside the volume omega, the rate of change, total rate of change of that is to be equal to 0. Now, I have my usual potato, which is, let's call it omega, and there are tractions on it. So these tractions are T. There are body forces B, and at any point on this, or for this whole volume omega, I'm going to say that Newton's second laws have to be valid. So what I am basically going to say is that rate of change of the total momentum, over this has to be equal to the total forces applied on this body. Now, total forces applied on this body is easy. So the total force is the sum of these body forces. So sum of these body forces, remember body forces are forces per unit volume. So if at any point the body force is B, at any point x at time t the body force is B, then that times dV gives you the body force in the small element of volume dV, and that integrated over the whole volume gives you the total vector force due to the body forces applied. So this is obvious. Then you have the total force, net force due to the surface tractions. So surface tractions, remember, are forces per unit area. So T multiplied by, let's say, this small element of area is ds. So T multiplied by ds gives you the total force acting on this small area, and you integrate that over the whole boundary delta omega, and you get the total surface tractions applied on the entire body. So this is the total force that is applied in the entire body. If we have concentrated forces, remember we subsume them inside T using the delta function. So concentrated forces are just special cases of surface tractions. We have already done that. So T includes both distributed surface tractions as well as concentrated forces. So this is the total amount of force, vector force, that is applied on this, and this has to be equal to rate of change of linear momentum. Now, momentum is specific momentum, as we were discussing in the last lecture, is V. So the total momentum is V times the mass of the small element dV. That, so this is the small element, its volume is dV. So mass of that is rho times dV. So this is specific momentum times dV integrated over the whole volume omega, rate of change of that. So this is the total momentum. Rate of change of the total momentum has to be equal to the total forces applied. This is my statement of Newton's second law, embodies the law of conservation of linear momentum. So this is where I am going to start from in this lecture. So this is where I start from. This is my law of conservation of linear momentum, or the Newton's second law, whatever you choose to call it. And this is a weak form because I am applying it over an extended volume omega, which can, however, be as small as you want. Now, we are going to deal with this in a step-by-step manner. Before doing that, let me deal a little bit with the left-hand side. I'll deal a little bit with the left-hand side, and while dealing with it, I will forget that I'm dealing with this specific case of particular case of the momentum. I will just assume that I'm dealing with a arbitrary quantity, rate of change of an arbitrary quantity, let's say A, over the same volume omega. So I'm dealing with this. We will put A as V later and see what happens. So when I'm doing this, there are a couple of steps that I can do. So I have already derived the mass balance equation. So I have already derived the fact that del this plus uh, this has to be equal to 0. So this is already derived. Make use of this to sort of reduce this to a more tractable form. Here we go. Uh, this is the total rate of change of A over the volume omega. Apply the Reynolds transport theorem to it. This is the first term. This is due to increase or uh, this is due to generation or destruction of rho A, and this is due to the flux of rho A through the bond. Now to this, because this is a surface integral, I convert it into a volume integral. Apply the divergence theorem. I have nk here, so I'll get xk here, and this is both are now in the volume integrals in the volume omega. So uh, del xk of a rho vk will lead to del a del xk, this is a fancy a, with a rho vk constant plus del xk of rho vk with the fancy a constant. So it can be broken into two parts. So the first part is here, the second part is here. Okay. And if you look at the second part, look at this part, then you will see that this is your balance of mass. So this we have already shown is equal to 0, which means that this is what we are left with. This is what we are left with. And this, you can see the term inside brackets. You can see that this is dA dt, which means that ddt of rho a dv, which was the left hand side to start with, is equal to this rho times dA dt. So we could take this ddt inside in some way because of the law of conservation of mass. Because of the law of conservation of mass, this ddt goes inside the integral, and this is what it turns out to be. In our case, in angular momentum, A is equal to V. So A is equal to V. So here also it's equal to V. So this is what we, sorry, this is for linear momentum, I'm sorry. So for linear momentum, A is equal to V, and therefore this is what we end up with. This is what we end up with. So this was the left hand side of the angular momentum equation. And I'm sorry, I keep messing it up. It's linear momentum, not angular momentum. So this is the statement of Newton's second law, balance of linear momentum. This was the statement. And we have now proved that this is so this is this, and the right hand side remains as it is. So we are now going to deal with the right hand side. Basically what we are going to do is we are going to deal with this term. And this term, we are going to apply the Cauchy relation. Remember, these fractions are applied on the boundaries, and we have the Cauchy relation which connects it with the stress through this. So this is what connects the tractions at the boundaries of omega to the stress. So I'm going to plug that in on the right hand side. So on the right hand side, I have, if I write it in initial notation, this is the first term, and the second term is this. Keep this second term undisturbed for the moment and write the first term as bring in the stress. Uh, when you apply this, you must remember this stress is at the boundary. So if when we had this potato and we have this tractions applied, this relation, Cauchy relation, relates this traction T to the stress right next to it, at a point right next to it on the boundary. So this is the boundary stress at the boundary connected to the traction and the normal at that point. So uh, this is over the boundary sigma ji nj, and again now I can apply to this the divergence theorem. So I have nj here. So if I apply the divergence theorem, I'll convert this into a volume integral with del x j del x j of sigma ji dv, plus of course the body force term remains. Okay, so this is what I will get. Both terms have now been converted into into volume integrals on the right hand side. So I have both terms converted into volume integrals. So I write them together. So this is rho dvi dt in initial notation dv or omega is equal to this. Apply the localization argument again, that if this has to be equal to this for no matter how small a volume omega is, then the only way that can happen is if they are equal at each and every point. That's a localization argument. I have explained what assumptions, what thought processes go behind the localization argument. All this we are assuming to be valid in our case. If you apply the localization argument, this is the strong form of the balance of linear momentum that you get. So this is the strong form of the balance of linear momentum. And this is also the law that governs the variation of the stress from point to point. At every point, this needs to be valid. This is the strong form. This needs to be valid at each and every point, and at each and every point, this has to be satisfied. You would realize that the total derivative of the velocity is nothing but the acceleration. So what you have on the right hand side is an inertial force. It's kind of density times the acceleration. It is inertial force per unit volume. It's inertial force per unit volume. That is what you have on the right hand side. And for most quasi-static problems, this is very small, or we assume this to be very small. So accelerations, if they are small, then this is the equilibrium equation, or the embodiment of the balance of linear momentum in strong form that my stresses must satisfy at each and every point in the body. And this is an extremely important equation. We'll keep calling this the equilibrium equation. The equilibrium equation is nothing but the strong form of the balance of linear momentum. What is a weak form? The weak form we have already dealt with here. This is the weak form of the balance of linear momentum. This is the weak form of the balance of linear momentum. This is over any extended volume omega, and applying the localization argument to this, we get the strong form, which is here. Okay, now uh, just a small point. If the accelerations on the right, so if this is not equal to 0 or not small, then you have to satisfy this equation. Erase the if they are not small, you have to satisfy this equation. The nature of this equation is significantly different from the nature of this equation that you use when the accelerations are small. So this is the quasi-static case. So the quasi-static equations have a very different character than the general equations of equilibrium. And solving this and solving this, though they might look very close uh, in spirit, they look very close. The solving this are completely different ball games. So uh, if you want to know more about how these kinds of equations are solved, you have to do a course on wave propagation in solids, and there this equation in all its glory will be taken into account. Whereas in this course, we will be satisfied with the quasi-static version. The right hand side will always be equal to 0. So this is my equilibrium equation, which is the strong form of the balance of linear momentum, and the weak form is here. Okay, so there's one more balance law that we need to do, and we do that in the next lecture.